Hello my dear students, welcome to Learning Chemistry is Easy and Fun. We are dealing with geometrical isomerism in this lesson number 10. In lesson 9 we have already dealt with structural isomerism and we are now going to do stereoisomerism under two separate headings, geometrical and optical. Geometrical isomerism, that is their geometry varies, their arrangement around the metal atom varies. The ligands have the same bonding arrangement with the metal atom, but their position with respect to each other changes. That is what is geometrical isomerism. So if I have ligands here, X and Y, right? These two may be opposite to each other. These two may be on the same side, right? For example, I'm going to take specific cases over here so that it's easier for you to understand. You know, geometrical isomerism in coordination compounds can be a bit tricky. So what I've done over here is I have drawn it as or put it up as a chart, and it's very easy. Believe me, following this chart it becomes very easy. At the same time, I will show it to you diagrammatically as well. We are taking up two types of cases over here, coordination number 4 and coordination number 6. What you need to understand over here is that we are talking about the position of the two ligands with respect to each other. You would be wondering why we are not talking about coordination number 2. Coordination number 2 means I have two ligands, right? Two ligands, whether they are same or they are different. Their position with respect to each other is the same. Whether I put it like this, whether I put it like this, with respect to each other is the same, right? So that means coordination number 2, geometrical isomerism, has no meaning. Isomers means I should have two or more forms differing in their position with respect to each other. That is what is geometrical isomerism, right? So I cannot have two different molecules. Let's talk about trigonal. So coordination number 3. So even if I assume that these three forms are different, right? Do you think it would make any difference to the molecule, right? This is trigonal planar arrangement. Is there any change in the molecule if the position of any one of these is changed? They're all the same. The bond angles are all the same, 120 degrees, right? So coordination number 2, coordination number 3 ruled out, right? That is why you will notice over here on the chart, I have not put coordination number 2 cross. Coordination number 3, nothing, right? They do not show geometrical isomerism. So we go on to coordination number 4. Coordination number 4 means there are two possible arrangements, right? We have done this under the structure of coordination compounds, tetrahedral and square planar. So let's first see the tetrahedral. Now I'm straight away going on to 4 different ligands, right? So this is how a tetrahedral arrangement is. All 109 degrees 28 minutes, and you can show these with the help of pencils. Better still, grab 4 pens or pencils in your hand, right? See, this is what I'm doing. There are 4 ligands. All 4 are different, but still the shape does not change no matter what the position of the ligand is. See? They are all the same. This remains the same. So that means again I cannot have two possible arrangements or two or more possible arrangements for these ligands. So when we have coordination compound with a tetrahedral arrangement, again no geometrical isomers here. Let's talk about square planner. Now for square planner, again, grab hold of 4 pencils, right? So what we've got over here, I'm going to take different cases, but just understand first, square planner is nothing but the page of your notebook cut in the form of a square. Simple. So 1, 2, 3 and 4. So we have a square here, right? And all of these are in one plane, right? Okay. Let's start with the different possible arrangements in the square planner. First, all 4 ligands are same. So in general, we say it as mx4. Now, when all 4 ligands are same, let's see, would you like to give it a try? Is there any difference in the arrangement, whether you put x here, here, anywhere? Their position with respect to each other is the same. There is no other possible arrangement. So would this show geometrical isomerism? No, absolutely right. So again, this is out of question for us, right? Come to the next one. mx3 and y. First of all, I'm talking about unidentate ligands over here. So I have mx3 and y. So this was our mx4. These can be anions. These can also be negative, these can also be neutral molecules, right? mx3y. 1, 2, 3 of one color and 1 of another color. Okay, let's say, so 1, 2, and would you like to put one more yellow over here? Okay, so there's a yellow. So 3 ligands are same and 1 ligand is different. Correct? Is there any other possible arrangement? Now let's see, if I remove this ligand and take the pink on the top and the yellow, is there any difference between this arrangement and the first arrangement? No, they are one and the same, right? So is there any GI possible, geometrical isomerism possible in mx3y arrangements? No. Let's go on to the next one. mx2, y2, right? 2 ligands of one type and 2 ligands of the other type. Yes, you got it right. I know, even without looking at the chart, if the concept is clear, this should make sense to you. Now just hold it like this, right? So you have 2 ligands of the same type on one side, 2 ligands of the same type on the other side. The other possibility is that they go opposite to each other, right? So I have this kind of an arrangement where the 2 yellows are on opposite side, the 2 pinks are on the opposite side, right? So that gives me 2 structures. 1. The 2 ligands of the same type are on the same side. 2 ligands, 2 ligands, right? This is called as the cis form. Cis means on the same side. The other, where the same ligands are on the opposite side, they are called as the trans form. Wondering what difference does it make, right? The ligands are the same, the bonding is the same. So why are we interested in cis and trans? An example, an interesting example is cisplatin. It's a coordination compound, as the name indicates, of platinum. Question for today, give me the formula for cisplatin. Cisplatin is something which is an anti-cancer agent and it is used for removing tumors. And interestingly, trans form, on the other hand, is toxic in nature. If it is used, then it can even turn poisonous. So on one hand, cisplatin is helping humanity. Trans form, on the other hand, can be equally dangerous, right? That makes studying geometrical isomerism very, very essential, right? So once we know the reason why we are studying, it becomes more interesting. Let's go on to the fourth form. So obviously mx2, y2, yes, it does show. Come to the fourth form, m, x, y, z, a. So I have 4 different ligands over here. So what is there? Is there a possibility? Let's check this as well. So what I do is I have 1, 2, 3 and 4. So here blue is between red and pink. At the same time, it could be like this. The pink being in between the 2 ligands. So what we've got over here is, that means how many different forms will be possible. So let me take yellow as my benchmark. So we keep yellow in place. 1. Pink is opposite to yellow. Red and blue are opposite. That's one form. Blue is opposite to yellow. That's the second form. Red is opposite to yellow. The third form. Swap the places of blue and pink. Does this become the fourth form? No, because this is the same as the third form, where pink was here and blue was on the top. Right? Is that clear? So that is why I have already drawn 2 forms over here. Third form, please draw it for me. Be careful. If you don't want to copy from the board, you can do that as well. If you don't want to copy from the board, please go ahead. Take 1 as the standard. Keep on alternating the other 3 ligands to give you the 3 isomers. Till now, I have spoken about unidentate ligands, right? Where one atom is the donor atom in the ligand. What if there are, yes, 2, right? What if there are 2 donor atoms and it forms a cyclic structure? Let's see one of the examples of that type as well under coordination number 4, right? I'm taking the example of a bidentate ligand, glycine atom, NH2, CH2, COO negative, where the nitrogen atom is the donor as well as the oxygen, right? So it's a bidentate ligand. The example that we are taking is glycine atom, platinum 2. So we've got to draw the geometrical isomers of this compound. What I've done over here is, I have drawn half of the molecule. It's still not complete because we've put only 1 set of the ligands, right? It's actually diglycinato. Now complete the molecule, right? Go ahead. So, NH2, CH2, C double bond O, and then we have O and then connected. So if you notice over here, it's the same ligands, the same donor atom facing each other. So which form will this be? Cis or trans? Very good. So the full name of this compound would be cis diglycinato platinum 2. Right? Can you draw the trans form of this particular compound? Try drawing it. I'll give you a hint over here. Just flip it around. Right? So the O goes up, the NH2 comes down. C double bond O goes up and CH2 comes down. Would you like to give it a try? The left side molecule remains the same. So PT, NH2, correct, CH2, why don't you pause the video, try it yourself rather than copying from the board. It's easy to copy. You can always start the video and do it. Yes, I like that. That you've given it a try yourself. You know, that's where the learning is. Now I said, just flip it around. Where what will happen is oxygen, C double bond O, perfect. And then we have CH2. See what we've done? And then we've got NH2 and there's a bond over here. Right? So what form will this be? Very good. This will be trans diglycinato-platinum. Very good. 2. So you are now clear with the geometrical isomerism for compounds with coordination number 4. Would you like to try geometrical isomerism for compounds with coordination number 6? You can just take various possibilities and see for yourself. I'm happy to see that you are able to relate to the topic. So let's continue with coordination number 6, geometrical isomerism. Now let's start with the geometrical isomerism for compounds with coordination number 6. And before we go on to coordination number 6, you have to remember that we talked about the octahedral shape of these coordination compounds. So what was there was that we have the 4 ligands in one plane and there are 2 ligands, one above this plane and one below this plane. So let me get it straight first. Yes, I've got it in place. Now you see over here 4 ligands, 1, 2, 3, 4 in one plane, one above it and one below it. And the angles, bond angles here as well as the bond angles here, all 90 degrees. Now see over here, so this makes a 3-dimensional arrangement. So let's see, let's take one by one. All 6 ligands are the same. So all 6 ligands are the same. So I've drawn purple lines over here and here goes my straw. All of them are same. Does it make any difference? No, whichever way you put it, they're all the same. So is GI, geometrical isomerism, possible in MSX6? Yes, strike it off. MX5Y, again, we've got one ligand as different. So let's suppose I have one ligand as different, right? So with respect to all the others, it is the same, correct? Whether I put it here or whether it occupies a position over here, whereas the 2 other ligands are occupying the top and the bottom position, right? So again, it does not show geometrical isomerism. Oh wow, that leaves us some space on the board, right? Otherwise it would have been too much to handle. Let's go on to MX4Y2. That means we've got 4 ligands of one type and 2 ligands of the other type. Yes, you can see it on the board. So let me explain it to you as well. So I'll have the satisfaction that I explained it, right? So I think I've got this card in place. So 4 ligands, 1, 2, 3, 4. It could be that they are neutral ligands, that is molecules with dipole, and the other 2 are negative or anionic ligands, or vice versa. Does not make a difference. We are concentrating presently only on unidentate ligands in this chart. Okay, I have not come to bidentate ligands as yet. So what we've got over here, 1, 2, 3, 4, 4 ligands in one plane, one above, one below. They are opposite to each other. One is lying above the plane of the paper, the other is below it, right? So this gives us our first arrangement, that is called as the, yes, the trans arrangement. Now how you will find it in your lot of books would be where they would have depicted this by means of dashed lines in order to indicate the shape to you so that there is more clarity, right? Got it? And then you go on to draw the three-dimensional. So this is here, here, and like this. I'm not doing it over here because then it makes it quite confusing. My target is to make you understand. I hope this should make it clear for all of you. So when we are talking about this, right? So this becomes one face. This becomes another triangular face. This becomes the third face, the fourth face, and so on. You must be wondering why I'm talking about it. You'll understand when we come to next. The second scenario in mx4, y2 is wherein what will happen is one of the ligands moves from the bottom position and occupies one of the positions here on the plane. The other continues to be on the top, right? Now, if you notice, instead of being at 180 degrees with respect to each other, they are at a bond angle of 90 degrees. Whereas one of our ligands has now moved down. Now, when we talk about this arrangement, we say this is cis. Now, this does not vary if I change the position of this ligand. I put it here. I put it here. With respect to the vertical one, it is still 90 degrees. So this kind of an arrangement is what we call as the cis arrangement in the case of octahedral complexes with unidentate ligands, right? Wouldn't it be better if you copy this down so that I'll have more space on the board to draw the others? Plus, as I always say, when you do it yourself, it remains embedded in your mind. So go ahead, grab sketch pens, different colors, draw these diagrams. Seriously telling you, you'll be happy to teach this topic to your classmates as well. Go ahead. I'm waiting for you to copy it. Now what happens when the ligands, it's mx4yz. That means instead of y2, you'll have total 3 types of ligands over here. There are in all 6, 4, 5, 6. The coordination number still remains 6, but I've got 3 different type of ligands. Yes, just change the y for, yes, so instead of y2 over here, this will become Z, this will become Z. So what we'll have over here is again 2 isomers. I am leaving this space blank for you to draw the structures yourself and name them the cis and the transform. In fact, interestingly, geometrical isomerism, because we have the cis isomers and the trans isomers, geometrical isomerism is also known as cis trans isomerism, right? Oh, so I definitely need more space on the board. Will you allow me that space? So let's come to the case mx3y3. That means I have 3 ligands of one type and 3 ligands of the other type. Now if you notice over here, I have put 2 words over here. They are not cis and trans. They are mer for meridional and fac for facial. Yes, right? So let's see. Meridional or meridian, something which is centered around the vertical line. That means something which is centered around the line in the middle. That's meridional. Facial, which is forming a face. Now this particular type of isomerism was a little difficult for me also to understand. I am being honest. So what I did was drew these on a paper. And if you can, Lay your hands on two pieces of paper and two different colored sketch pens. I bet you'll be able to understand this as well. So let's try the first one. Where we've got is, what we've got is the three ligands. The X ones are here. So I've got 1, 2, 3 of one color, right? These three are in the plane, on the plane of the paper. The fourth ligand is different, right? That's, I've put it in orange. And in order to signify the orange, two other ligands of orange color. So this is my yellow straw here. That's the closest I could get. So now your ligand, the yellow ligands, they are focused around this axis, right? So if I join over here and here, it forms a triangle where one of the sides of the triangle is the meridian, the line passing through the center of this octahedral. So what we've got is the mer isomerism, right? Or the mer isomer. Next is, we change the positions. Yes. So I've got here the two purple ones. Of course, they still remain in the plane of the paper. Now, the yellow one, it has changed its position. From the bottom, it says, no, I want to rest for a while. I can't remain standing. So it says, okay, let's swap the places. So we've got the two yellow ones here. The third yellow one on the top. And where does the purple one go? At the bottom, right? Now if you see the three yellow ones, join them. Here, 1, 2 and 3. So it forms the face of this octahedral, right? So let me show it to you like this. So if I connect it over here, right, this is how it will be. So it forms the shape. Let me put it more correct. You see over here, I've got the three yellow ones and this is the face that we've got, right? So that is why this is called the facial isomer, the facial form of the geometrical isomer of octahedral compounds with the formula mx3y3. Now here I'm not specifying what is x or y. If x are the anionic ligands, then y are the neutral molecules, or vice versa, as you may choose to express. Here now, if I have to show you the same thing on paper, probably I would join it like this, right? And then we've got to shade 1, 2, 3. This is my meridional, right? Sorry if I've got the pronunciation wrong. 1, 2, 3, 4 is in one plane. And what have we got over here? This and this, right? So your y could be up and x could be down. Does that make a difference to the isomer? Does it change? Does it give me a new isomer? No, it doesn't, right? So we've got the two different isomers with this formula. Let's talk about bidentate ligands. Let's touch base on that as well. Did you remember to copy this? Don't forget, it will come in really handy if you can draw it, especially on a calendar. Just draw it on a big piece of paper. Go through it just before the exam. You don't need to read the whole text. I can promise you this. Now I'm taking a very simple example of compounds with coordination number 6 but having bidentate ligands. That means there are two donor atoms. Here the bidentate ligand is ethane 1,2-diamine. The structure is denoted over here. Now this is a symmetrical bidentate ligand because both here symmetrical means, see, the two parts are mirror images of each other, correct? So I've got nitrogen and nitrogen as the donor atom. How do you view it now? The only thing is you have to see it like wherein your two ligands here are replaced by one ligand, but this is one unit. So we've got nitrogen as the donor, nitrogen as the donor. So I've got one set over here. In the texts, you will not see it written as En like I have written over here. This I put for clarity. How do we usually denote it is we do not show the N. Here we've got a straight line. Here we've got a curve and En. Right? Here the breaks indicate the position of nitrogen as the donor. Right? I hope this makes it clear. Nitrogen I have put only to make it clearer to you, like I have written over here. I'll let it remain like this for the sake of clarity. Once you've got a hang of this, then you can put it like this. Now connect the dots. Simple to get the shape. So we've got this is the plane of the paper. One chlorine above it. This is along the axis, correct? Now the two chlorine Cl are close to each other. So this becomes my cis form. Even the two En ligands are also facing each other, right? So not facing, they are close to each other. So the cis form, it's called as the same side. What about the opposite one? So we're talking about the trans. So they come at loggerheads. They now face each other. Only thing is, just imagine like this. So I have got nitrogen, nitrogen, nitrogen as the donor, right? Simple. This makes it clear. 4 ligands for you. It's clear, this structure. Now draw the chlorine. Now draw the Cl. Right over here. One above the plane of the paper, one below the plane of the paper. So this is very much like this case, right? Now, in order to complete the molecule, let me make it a little more easy for you. Just rub out the N and I will represent En over here and I will represent En over here, meaning to say we've got the donor atoms, nitrogen over here of the ethane 1,2-diamine. Let's complete the structure. If you want to show it, there we go. We've got the octahedral structure in place. The two chlorine are opposite to each other. The two bidentate ligands are opposite to each other. And that gives us the trans form of this compound. So we've got geometrical isomerism, coordination number 4, coordination number 6. Now comes the interesting bit. I am challenging you. If you have understood this topic well, I challenge you to attempt questions from any of the book that you have, any of the textbook or reference book that you have, and attempt questions on structural isomerism, because we've already done that in lesson 9, and geometrical isomerism. Just try attempting not more, just 3 or 4 questions. And do send me a smiley in the comment section if you are able to understand this. Happy studying to all of you. See you in the next lesson.